back to Wise Weather Wise with your host, the Big Weather Guy. I thank you very much for watching, and if you have any questions, please do not hesitate to leave it in the comments down below, and I will do my best to answer it. And if you are enjoying these lessons, I would humbly ask that you consider subscribing to my channel and liking the video. This is episode number 2, and today we will be discussing some of the basics about this thin little skin that our planet has, the atmosphere. What is the atmosphere? Why is it here? What is its favorite color? The answer to that, of course, is blue. And is there any truth to the rumor that the atmosphere actually wrote the works of William Shakespeare? Spoiler alert, no, that is not true. It was Christopher Marlowe that wrote the works of Shakespeare. So, what makes the atmosphere so special? To make a long story short, without the atmosphere, there would be no weather, and hence this series of lectures would be incredibly pointless. Perhaps worst of all, there would be no living things on Earth to enjoy my corny jokes. And what a tragedy that would be. Simply put, the atmosphere is why we are alive and why we have weather. The atmosphere is, when you come down to it, just a bunch of air. Of course, it is slightly more complicated than that. First of all, a few facts about the Earth's atmosphere. The mass of all of the air in the atmosphere is 5.5 quadrillion tons. The importance of all that weight pushing down on everything will be discussed in more detail in the next episode in regards to atmospheric pressure. All of that mass is actually kept in place by the gravitational force of the Earth. As was mentioned in the first episode, the ozone layer is a vital component of maintaining life on Earth by absorbing ultraviolet radiation from the sun. Further, that atmosphere also plays another vital life-sustaining role by regulating the temperature of the planet. Without it, daytime temperatures would rise to a rather warm 250 degrees Fahrenheit and drop to a brisk negative 208 degrees Fahrenheit at night. Finally, as you will all remember from your middle school earth science class, the atmosphere is made up mostly of nitrogen, 78%, with about 21% oxygen, and just shy of 1% argon. Then there are the small trace gases such as methane, hydrogen, neon, helium, and carbon dioxide, among some others. Another flashback that you may remember from middle school, we will just briefly visit, is a simple cross section of how the Earth's atmosphere is broken up, like a layer cake. There are 5 main layers from the Earth's surface as you travel upwards: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Between each layer, there is a boundary layer that uses the name pause, or tropopause, stratopause, etc. Let's take a look at each layer in a bit more detail. First up is the troposphere. This is the layer where the vast majority of weather occurs, and so it is the most interesting layer in this lecture series. The troposphere is generally about 10 to 12 kilometers thick, or about 7 or 8 miles, but it does vary depending upon where you are on Earth. We will discuss that in more detail in the next slide. The summit of Mount Everest sits just shy of 9 kilometers above sea level, and so it is just about the top of the troposphere, and many passenger airliners fly in the upper reaches of the troposphere as well. As a general rule, as you go up through the troposphere, the temperature decreases. There are notable exceptions called temperature inversions that will be discussed more in later lectures. Previously, we learned that all of the air in the atmosphere weighs about 5.5 quadrillion tons, and about 75% of all that mass is in the troposphere, in the lowest 7 or 8 miles of the atmosphere. As previously mentioned, at the top of each layer, there lies the pause. When looking at the top of the troposphere, we find the tropopause. The tropopause is the line of demarcation of when temperature trend reverses. Again, the temperature in the troposphere drops as you go up, and in the stratosphere, as we will discuss, the temperature begins to rise. So the tropopause acts as a natural cap on air that prevents it from rising any further. In the diagram on the left, you can see that the height of the tropopause is variable depending on where on Earth you are. This is because of the rotation of the Earth and the higher relative speed of rotation at the equator. If you think about it like a perfectly spherical balloon, and if you spin that balloon on a tabletop, the top and the bottom will press down, and the sides of the balloon will bulge out because of the centrifugal force. We'll dive a bit more into this in a future lecture when we discuss wind patterns. One of the most interesting demonstrations of the presence of the tropopause is readily visible quite often in the forms of the cumulonimbus cloud or a thundercloud. The great upward momentum of a thunderstorm can oftentimes reach so high in the troposphere that the clouds impinge on the tropopause and begin to spread out in all directions, forming what's called the anvil of a thunderstorm. Particularly strong cells can even have a portion of the convective column that can temporarily push up through the tropopause and into the lower stratosphere, called an overshooting top. Here are a couple of beautiful examples. One photo taken here from the International Space Station, and another taken from a weather research aircraft. The next time you have a good line of sight on a thunderstorm, you should look for the anvil. Moving up past the tropopause, we find ourselves now in the stratosphere. The stratosphere averages about 25 miles thick, and it's stratified by density and temperature. The coldest temperatures and the most dense air lays here at the bottom, and the layers at the bottom of the layer, and the temperature increases as you rise through that layer. The stratosphere is where the vast majority of the atmospheric ozone is located that protects the Earth's surface from the sun's ultraviolet radiation. The stratosphere is also home to some really interesting phenomena, such as blue jet lightning, that we will discuss in a later lecture when we explore all different types of lightning. Next up, we have the mesosphere. This layer is not very well understood but in comparison to the other layers because it is too high for aircraft and balloons to study and too low to be studied by satellites. From time to time, there are small rockets that fly into and through this layer, but that is relatively rare. When I lived in Alaska, I was lucky enough to work at the Geophysical Institute at the University in Fairbanks. The GI had a rocket program that fired instrumented rockets up into the upper atmosphere to study the aurora borealis. It was very cool to see the launches. Anyway, back to the mesosphere. There are a lot of interesting phenomena that occur here. It is in the mesosphere that the density of the atmosphere begins to be high enough to really affect inbound spacecraft or material. For example, when a satellite deorbits or when a meteorite hits the atmosphere, it is the mesosphere where it typically burns up. There have actually been traces of iron from vaporized meteors that have been detected in the mesosphere. Also, there are very strange lightning-related phenomena, such as sprites, which we will discuss later, and then the high-altitude noctilucent clouds, which are quite a sight to see if you are lucky enough to see them. We'll discuss those more in a later lecture about clouds. The fourth layer is called the thermosphere. There is not much in the way of weather here, of course, but it is a very active layer for many other things. Temperatures are highly variable because there isn't much in the way of air molecules around to measure, but areas where solar radiation does interact and ionize the molecules can reach more than 2500 degrees centigrade. The International Space Station orbits in the thermosphere, and other manned spacecraft orbit in this region as well. This is also the region where the aurora is, and the ionosphere layers, where the solar energy ionizes the sparse gas. Those layers are very vital in long-range communications, and low-frequency radio signals can actually bounce off these layers and come back to Earth long distances from where they were created. Finally, we come to the exosphere. Firm understanding of this layer is quite fuzzy, literally. There is debate amongst scientists whether it is part of space or part of the atmosphere. The layer begins anywhere from 500 to 1,000 miles above the Earth's surface, depending upon the strength of the solar wind. The stream of X-ray and ultraviolet radiation from the sun presses on the exosphere and pushes it towards the Earth, and so it's somewhat malleable, if you want to think of it that way. As for the upper edge of the exosphere, that again is up for debate. One theory is that the edge of the exosphere is at an altitude of about 120,000 miles, which is where the gravitational force exerted by the Earth tips over into the forces external to the Earth, such as radiational pressure or the gravitational force of the moon or other bodies. Very faint ultraviolet glow has been detected by special cameras that can detect the UV radiation scattered by hydrogen atoms under solar bombardment, such as the faint glow seen in this image taken from the moon by the astronauts of the Apollo 16 mission. So that does it for this lecture of basics about our atmosphere, and as usual, I will leave you with the vital point to remember. The atmosphere is a highly complex and widely varying system that makes life possible on Earth by moderating the energy the planet receives from the sun and giving us air to breathe. It also gives us weather. Thank you so much for watching, and I hope that you have enjoyed it and have learned something. If you want to watch the previous lecture or want to be alerted to when subsequent lectures are posted, please visit my channel page, clicking on the Weather Wise playlist. Please consider subscribing to the channel so that you can be alerted of new videos, including forecast discussions of upcoming weather events and discussions of past weather events. If you have any questions or comments, I would love for you to post them under the video and I will do my best to answer them. If I've gotten something wrong, please let me know so I can correct it. Next time, in episode 3, we will take principles from the first two lectures and apply them to the subject of the ideal gas equation and atmospheric pressure, which is one of the most elementary variables that influences so much of our weather. Until then, have a good day, and thanks for watching. Cheers.